Hello, good evening. How are you? My name is Jalam Mehman and I'm teacher for this course. And recently we have done the course on the laminar pipe flow. And if you didn't do that thing, please, I highly recommend that you should go through that workshop tutorial because it covers all the things in a single section. Okay. So now the second workshop is the turbulent pipe flow, the same like procedure for the geometry and the meshing sort of, but the here the physics is different. Now it's a turbulent pipe flow where the Reynolds number is greater than 4000, and here I will be studying or teaching you the turbulence model, difference on the results, and the Y plus as well. And we will take care of the Y plus as well on the meshing part. And the validation of the various empirical correlations that you will see in the fluid dynamics book. So I will show you them. Okay, so starting with the problem description that we will be solving the problem at the Reynolds number is equal to 10,000 CFD study. And I have taken the length is equal to 16 meters and diameter is equal to 0.2 meter and L by D is 80. Okay. And I have taken the velocity is equal to 1 meter per second, density 1000 kilogram per meter cube, and the viscosity is a result of the solution of the Reynolds number equation. I cannot give the every parameter directly, so it should match the Reynolds number value. So for example, 10,000 for Reynolds number, density is a 1000, multiply with the velocity is equal to 1 meter per second, diameter is equal to 0.2 and divided by the viscosity. So viscosity becomes 1000 into the 1000 into 0.2 divided by 10,000. So dividing them we get the 10 and this becomes the 0.02 kilogram meter second or Pascal second. And the formula for the CF is the same as we have done in the, or you can check it from the books, but this is a formula that we already discussed in the laminar pipe flow. And the CF is found out from the watt shear stress divided by 1 upon 2 rho V square. And the CF is the coefficient of friction and the F is the Darcy friction factor that you see in the hydraulics books like in the Darcy, like internal flows in the pipe. And the CF is a coefficient of friction that usually you see in the aerodynamics. So when any people who is working on the water as a working fluid, they use the Darcy friction factor, and any person who is working in the aerodynamics field, they will use a CF. And we will draw the same velocity profiles, pressure drop, friction factor, and the coefficient of friction, but this time they will be entirely different as the physics is now different. And we will compare them not with the analytical solution but with the empirical. So what is empirical? Empirical is actually a data from the experiments that is correlated, and we fit them the curves on those data points and we get the equations. And from those equations, when I put the any value for the given Reynolds number, I can get the value of the those parameters. And definitely we will post-process the results as well. Okay. So now let's go to the next slide, and here you can see that we have the definition for Reynolds number, and the same definition that we know about very well. The flow is laminar when Reynolds number is less than 2300, flow is turbulent when Reynolds number is greater than 4000. So if I inject a dye that if the disturbance is there, then flow is turbulent, and if the flow is in a straight lamina or lamina straight line, then the flow is laminar. So the range is of Reynolds number is given there. Okay. Now as far as the developing region like a theory is concerned, so we have to see that for turbulent flow, what will be the value of the developing region or the entrance region, and what will be the value or what will be the like a section where the flow is fully developed. So if I I'm showing you a picture here. If you take a look here, you can see in case of laminar flow, when the Reynolds number is less than 2300, so in that case the flow is like a behaving in a lamina, and the flow is the velocity profile that is like when the flow is fully developed, it means that the flow is not changing in the x direction, but the velocity changes in the y direction, r direction. So what does it mean by that flow not changing in the direction? Means that if I take the one point on this profile and I draw the second profile here, but it's the same axial, the radial location, so axially there will be no change. So du by dx means that the u is 0, u1 and u2 they are equal, so their difference 0, and we get the du by dx is equal to 0. But and the profile is parabolic, okay, and the maximum velocity is equal to the maximum velocity is equal to twice the average velocity. That is if you can average this profile by adding all values and divided by the number of values, are the same as the inlet velocity at the inlet of the pipe. And in the turbulent flow, the flow is turbulent, like Reynolds number is greater than like a 4000, which is surely the turbulent flow. But at 2300, the flow starts to change from our transitioning. It starts to happen. So flow is starting to change from laminar to turbulent. And in this case, the velocity profile is highly different. It is like sharp gradients on the wall. They are very, very sharp as compared to the laminar flow. But in the middle region, there is a maximum velocity is there, but that is like a more flat than the laminar flow. And the velocity varies like 1.2, 1.1 between those values depending on the Reynolds number. So the same like a theory is still valid, which is that when the du by dx is 0, okay, so the velocity is only function of the radial coordinates, so it's only changing around the radius. And but correlation is different. For example, for laminar flow, the correlation was L by D is here, was equal to the 0.05 into RE. But here this is the L by D is equal to the 1.359 into RED, 1.1 by 4. RED means is a Reynolds number based on the diameter. So for our case, the L by D there where the flow becomes fully developed, like a entrance region, is the L by D is equal to 13.59. L by D is equal to 13.59, and that is like a higher value than the, like if you take a look on the laminar pipe flow around number 100, where the value was 5. So 13.59, and if I take the diameter, like a diameter in our case is a 0.2 meters. So in this case, the entrance length, this is only entrance length, this is equal to the 13.59 into the 0.2. This becomes a 2.718 meters. So out of 16 meters, 2.718 meters are the entrance region portion. But I have the experience with the laminar flow and turbulent flow as well. The actual values of CFD, they can vary depending on the turbulence model, and generally speaking, they are not exactly same as these empirical correlations. And in my experience, usually speaking, they are double the values. So now, if you want to make a geometry, so the geometry should be long enough, lengthwise, so that it can entrance region can be modeled properly. Like for example, double value will be around 6 meters, and there should be enough length here where I can study the flow. And secondly, if I change the Reynolds number from 10,000 to 30,000, the length of entrance region will increase by the factor of 3. So this becomes 18 meters. So it means that you should be careful about the pipe length when you are increasing the Reynolds number, because entrance length can be very, very high for when the flow has a high Reynolds number. The solution would be that I have shown in the some in the coming sections, that you can reduce the pipe length by applying the same velocity profile through the UDF or through the expression, or there is a profile file, okay, that you can now the profile file can can only tackle the simple profile like these ones. They are handled very well. Expression can handle them in a more with the more options there, and it has a more functionality there. And UDF is the ultimate thing, that is like you are writing the C code and then you are coupling with the Fluent. So I can only model the few meters upstream and apply this profile exactly on that portion, like a modeling up to here, and I apply the velocity profile over there. Okay, whatever profile it's a laminar profile, a turbulent pipe flow profile, whatever I want to model. So this will shorten the length, and I can only add the 5 to 10 meters length, and I can solve the problem with because we are interested in the fully developed region always. Okay. So now here is the analytical. Why I'm saying analytical as well, because these formulas, when you use them, they end up being put into the these theoretical formulas, analytical formulas. But the factors here the F factor, which is delta P. So delta P is the same we have discussed in the laminar pipe flow case. So let me show you. The laminar pipe flow, the formulas we had were delta P was equal to the 32 mu L U average upon D square. So this is same actually. So what we change here, here if you take a look here, this is the same. The F into L by D into density velocity squared divided by 2. So D, small d is shown here, this is capital D. The small l is shown, this L is a capital length. This is the capital letter, this is the same length of the pipe and diameter. But what we are tend to use in turbulent flow is that we use the velocity profile is simple, very simple in the case of laminar flow, but the velocity profile is slightly complicated. It depends on the many things there, on the turbulence as well. So we don't put directly these factors, but instead of that we put the equations. So for example, here, because we know that the velocity profile we know about in the laminar flow, so we put their values there, and we just take derivative of the wall shear stress and or the shear stress, and we get the end up with the simple formulas. But here I will rather be using the formulas in this form. Okay. So okay, let's discuss here. So if I show you the Moody's diagram that you can find out in any book, and the Reynolds number is equal to the 10,000. That is the 10,000 means this is equal to the 10 power 4. So we are here. Okay. So take this value up to here. This is the smooth pipe. We are not modeling any roughness there, and the roughness is given as a relative roughness, that is the epsilon upon D. So what does it mean? It means that if the pipe is there and we have the some roughness there, roughness that you cannot see with your naked eye, but with the microscopic apparatus, so the roughness will appear. They are random actually, they will not be of same size. I'm just giving example. So this is the roughness height epsilon, and pipe diameter is D. So the values that are important right now is in terms of the relative value of the epsilon by the D. This is called the relative pipe roughness. Okay. So this is given here. So if you take a look here, the value of the friction factor for smooth pipe with the Reynolds number is equal to 10,000. It is around 0.032. Okay. So same value is given here. So this is exactly value taken from the correlation here. Okay. So this is from this correlation, and there are two correlations that we can use for our purpose. So one is the Colley-Brooke equation, one is the AC Holland 1983. So both of them will give you the almost like a similar data. So I use the first case, which is the second case. Okay. And important thing is that actually why I didn't use the second one, because it contains the F in the both terms, and this requires a numerical method to solve. But this can be solved very easily by putting the value of epsilon by D is equal to 0. Reynolds number is equal to 10 power 4, and Reynolds 6.9 divided by 10,000, and then take the logarithm, natural logarithm, then multiply the 1.9, then inverse, and then square. The value will become positive, and we get the values like these ones. Okay. Same can be done with this equation, but then you have to solve that one numerically in the Maple or MATLAB, or maybe in some online equation solver, but that's not to be solved on the paper. Okay, then this is the a chart from the Sengel's book, and here you can see the smooth surface, all the values for Reynolds number 10 power 6. So for various epsilon by d, you can find out the friction factor there, and friction factor will tend to decrease. It is like highest in the laminar flow, then it's a dropping there, then again it increases in the case of the transitional flow, and afterwards it will start to drop again. Okay, so here I have found out the value of Darcy friction factor. From that we can find out the CF, that is equal to the F divided by 4, and that value we can directly compute in the Fluent, okay, in CFD software. And the formula for CF actually is this one. And so in the CFD software we will put this formula, wall shear stress divided by this term, and we get a CF value there, and then we compare with the CF value we got from this empirical correlation. This empirical correlation means the excellent data, but definitely this is the best fit curve on that data from the experiments. Okay, now I'm using the pressure drop from the Darcy's formula using the Darcy friction factor, and the formula is still same. The formula is delta P is equal to, this is delta P actually. So this is equal to the friction factor L by D V square upon 2G. So if you take a look here, this is a F here, and then we have the L by D. The L by D is equal to the 16 upon 0.2, and this is the density velocity square upon 2. So density is 1000, velocity is equal to the 1, so 1 meter square divided by 2. So we are getting the pressure drop of 1234.64 pascals. Okay, let me calculate on the screen. So calculator. Okay, let me do it again. 0.030866 into 1000 into 16 divided by 2 and divided by 0.2. So 123.64. Okay. So this pressure drop, but please note that this pressure drop should be compared. This is for the whole pipe, but I would suggest that in the CFD, after when the flow becomes fully developed, so that will be after like 5 meters, 6 meters. So make a plane there, and after that measure the data for the pressure drop, and for the same length you should put the value here. So let's say 16 meter minus 6 meters for the when the flow is like developing there or entrance region. So use the 10 meters here, and same length should be used in the CFD as well. Okay, so now here you can see all the equations, like pressure drop is rho GHL, this is a pressure loss or the head loss, and that can be also put into this equation form, 4 times the tau wall L by D. This is the same equation we derived earlier as well in the laminar pipe flow, and you can find out the pressure head loss through this formula, which is same as the pressure drop P1 minus P2, and this can also be found out from the friction factor L by D and V square upon 2G. Okay, but here the friction factor is not directly like a function of the Reynolds number like in the laminar pipe flow, but it's a function of the Reynolds number plus the epsilon upon D. If the epsilon upon D is 0, then this will be simply a function of Reynolds number, but not exactly. The values are same as the laminar pipe flow. So just like an idea here that what does it mean by the when the flow is turbulent. So what's the difference between the laminar flow and turbulent flow, and how then the modeling approaches for CFD will be different for these two cases. So I will explain that thing as well now. So the one of the most difference that you will feel is that in laminar flow, the flow is in the lamina and there are no disturbances. Okay. But in turbulent flow, that is the name suggests that there is disturbances or the flow is chaotic. So that is evident from the velocity profile as well. You can see that the red color is showing the mean velocity, while the black color actually is the actual velocity profile, and that is we call that one instantaneous velocity profile, and every time you check it on the same location, like the same vertical line, you will see that every time they will be producing the different velocity profiles. So every time the instantaneous velocity will be different. Okay. So what does it mean? It means that the mean velocity might be stay the same, but the changes from the mean velocity profile will always be different. That's the nature of the turbulent flow. Now this means that if I want to predict the turbulent flow, I have to not only solve like we do in the laminar flow, we solve the equations for the velocity profile like the du by dy, dy or du by dr actually. So we write it down as a dy because we are solving in the xy coordinates, but the y coordinate is actually representing the radial coordinates, and the x is in the axial direction. So that when you solve the problem as a two-dimensional, otherwise three-dimensional, everything is like a x, y, z. So here we have to take care of this change as well. So that is called the fluctuating component. Okay. So now I can put my u as a function of t, that is the instantaneous velocity profile, is equal to the u bar, u average, and the u dash. So this is the average velocity is over here, and any change that is we are modeling that is from the mean velocity is the u bar, and that definitely is not a constant value. But when we solve the problem using the RANS or the eddy viscosity models that we usually use for the CFD, like a k epsilon, k omega, these models they assume that this change is constant. So that is like a one approximation that you get in the CFD is the truncation error, that is a mesh error, or you are like leaving the high order derivative terms on the your in your equations, and also you have the finite like a size of the cells. It cannot go to the zero. And second error that is coming is like from turbulence. So that's why whenever you solve through RANS, you can expect the error like a range maybe from 5 to 15%. So I always try to keep the error less than 10%, but sometimes it may be higher depending on the flow nature. So now question is that how this can be solved in the CFD and how to approach that thing in the analytical approach. So that both things we will see here. Okay. Okay, definitely in the analytical approach, when you solve the problem, we are like comparing the, like we are getting the value for the average velocity that we are going to compare in the CFD as well. But that average velocity that we are getting is actually has effect from the turbulence as well. Okay. Okay, so now this is like a turbulence modeling discussion will be here. So this will be like a very brief, and you can like watch my other lectures maybe in this course. So in the laminar flow, we have the parabolic velocity profile that is represented by this equation here. Okay, this equation. But for the case of the turbulent boundary layer, and the thing you can see here, that in the laminar pipe flow, the maximum velocity is equal to the twice the mean velocity. But in turbulent flow, that is different is like is on the lower side, but it has a steep gradient on the wall side that I discussed earlier also. It has a steep gradient on the wall, okay, like here, and but inside, like in the main or the core region, that is becoming almost straight, okay. And also you can see the one kink here, something like a discontinuity here. This is a part of the turbulent pipe flow as well, and this is given by the relationship here is given by, like here you can see this is the u maximum. So I can write it down for the laminar flow u upon u maximum, and this is also like a function of r. So is equal to the 1 minus r square upon r square. But here almost similar thing, 1 minus r upon r, but the whole power is a 1 upon n. So n is like an index, and that will vary for the most of the flows, and usually speaking, this is 7 for the most of the flows, but it value actually varies from lower value to high values, and depending on Reynolds number. So we discussed that thing. And when you solve any turbulent pipe flow or any turbulent flow, it has the 3 to 4 layers. The one is the viscous layer, one is the buffer layer, one is the overlap layer or the logarithm layer, and one is the outer layer or the turbulent layer. So for this, like a first layer, viscous sublayer, the y plus should be less around 1 or less than 5, okay, less than 5. The buffer layer starts from the y plus 30 5 to 30, okay. And overlap layer, it is from like 30 to 100 or maybe up to 200, okay, depending on the flow. And then turbulent layer can be from 200 to 1000, okay. So if you want to resolve the because the maximum shear stress is in the wall region where we are going to be having the maximum loss in the pressure loss as well. So if you are going to predict the very accurate values for the pressure drop, the coefficient of friction or the Darcy friction factor, then you should resolve your viscous sublayer. So for that we will keep the y plus 1. And also I will give you one more example where I will keep the y plus around 10. I will compare that if the first cell height is not in the viscous sublayer but in the buffer layer, what will happen. And maybe you can try one more case yourself if you keep the y plus greater than 30 or equal to 30. And the flow equations are the exactly same, that is the convection term, then the pressure drop and the shear stress term. And as you know that the velocity is there is no gradient in the fluid envelope flow in the x direction, so this term is 0, and there is no velocity in the v direction, so this term also is a 0. So only terms we are left are these terms here. And now thing is that this term is very easy to understand, but this term, so what we did is that we put the u as this is the instantaneous velocity profile, and that's a function of time is equal to the u bar, u mean plus the u dash, that is a fluctuating component. And once you simplify them with the Reynolds averaging, you will get that this term here. This is the additional term if you compare with this equation. So this term is called the Reynolds stresses, and with some assumptions and some formulas, we can convert this formula, this term into this form. So it means that what we did is that we have actually converted the Reynolds stresses into the mean velocity components, and now our task is to find out the this eddy viscosity. Okay, so eddy viscosity we have to find out from the turbulence modeling, and those turbulence models actually are either the mu t or the kinematic viscosity will be the nu t. So that can be found out from the various relationship between the k epsilon or the k omega. And in the SA model, this is done with the help of the modified turbulent viscosity. So once we find out these properties, we can put in the formula, and we get the values for the this what we call as a turbulent viscosity. Let me show you that the formula for that. For example, this is the equation for the k epsilon model that are used also in the Fluent as well. So the equation for the k and epsilon, they are similar, and they are not derived directly from the first principles. K is derivation is there, like you can see here. So, but the epsilon equation, this is the rate of dissipation of the turbulent kinetic energy. So this is directly inferred from the k equation. So just change the k with the epsilon and balance of the terms, so that we have to put the extra terms like a p is production is now added with the epsilon. So now we have to balance the equation like a units. So these two terms are added here. Okay, and so I was talking about that how we can find out the turbulent viscosity. So for the k epsilon model, the equation is the density multiplied with the c mu. C mu is like a 0.09 for channel flows, and k square upon epsilon. So we solve these two equations, but these two equations, if you take a look here, these equations basically they are again in terms of the mean velocities, and they like a k and epsilon, like a k is we can find it out from the a mean velocity. So it means that we have changed everything again back to the mean velocity, and once we solve the k and epsilon, we just put them into the mu t relationship, and the mu t will be put into the equation over here, and the du by dy is already calculated, and du by dx and du by dx and v and u, they are already calculated. So just put into equation, and we get the u instantaneous velocity. But that is with like I told you, this term that we are putting here, it assumes that the fluctuating component is the disturbance is a constant value on the both sides, on the negative side and positive side, and that does not change with a turbulence. So that's a big assumption, but this is how the eddy viscosity models works. Okay. So now go back to our presentation that is on the turbulent pipe flow, and here we are. So you get the idea that how we find out the turbulent viscosity, and that's a basic like a principle of all the eddy viscosity turbulence models. So this is an equation that we are interested for to find out the value of the nu t. Okay, now as far as the these regions are concerned, like overlap region, buffer layer, and turbulent layer. So the equation for the viscous sublayer are these ones. 1 minute. Okay, so for the viscous sublayer, the u plus is equal to y plus. I will explain what is u plus y plus, and the u upon u plus, that is the u upon u star. This is the friction velocity actually. This is equal to the this term is also equal to the u plus. Okay, and this term is basically a y plus. So to solve this in through CFD, we have to this is implemented in the software. We don't need to select ourselves. So if you are solving with the wall function, then this equation will be activated, and if you are solving with the y plus equal to or less than 1, then this equation will be implemented. So how this is implemented? Actually, this is a mesh. So what we are doing is that we are solving the equation of the momentum equation we're solving on these cells. So if you are directly on the wall, like a no slip condition is there, the no slip condition provided from the wall. But the thing is that the first cell height, that is not exactly on the wall. Okay, in case of finite difference, the first node will be on the wall. That's a different thing. In the finite volume, the first cell is not directly on the wall. So how to find out the value of this first cell? So that is found out from finding out the shear stress on the wall, like on the bottom. And then we have to find out the value of the velocity that is on the first cell center will be there. That is if you are in the y plus 1, then I will use the y plus, u plus is equal to y plus. So if the y plus is 1, then the u plus will be equal to the 1. And this is the u upon u tau is equal to 1. So u can be found out by the 1 into the u tau. So you can find out the friction velocity, and the friction velocity is given by the square root of the wall shear stress divided by density. So now once you find out this value, then you can find out the velocity from there, and that the tau wall actually is coming from the wall conditions. So we can now put the velocity at these different locations, and these velocities may be different because the y plus will be maybe different, and maybe the friction velocity is different. Okay, so with the friction velocity different, y plus will be different, and so the u is different. Then after once we provided the properties here, then these points will be solved numerically by the solver. Okay, so that's why this is a very important thing to do. And when we are in the viscous, in the a log layer, in that case, we will use this equation to provide the value of the u there. Okay, and in the fully turbulent layer, that is outside, when the flow is it's almost reaching the middle region, and that part, this formula is applied here. Okay, okay. One more thing is that when we are talking about turbulent flow, this is different from the laminar flow. Laminar flow profile is a parabolic that you can see here. But the profile for laminar flow, it depends on the Reynolds number. So Reynolds number variation will change the a profile shape as well. So this is not a case in the laminar flow. Laminar flow will be having same profile, but the values pressure drop and these things can vary. But in case of turbulent flow, the velocity profile itself is actually varying. Okay, so its shape is not constant. So how this is done? This is done by the index of the formula n and Reynolds number. So they I've taken from some reference. I don't remember the reference name, but this is what I copied directly from there. So when the Reynolds number is a 4000, that is very close to the the turbulent flow lower limit. At this point, the Reynolds number, the n is equal to 6. But if you go on the higher side, that is a fully turbulent flow. At this point, in internal flow, the turbulent flow start at the 4000 Reynolds number. but this is very high Reynolds number. So at this point, the value is 10. So now the thing is that to find out the value for index for our own case, we have to like use interpolation and find out the value for n for our case. So what I did is that I have the this relationship with me. So Reynolds number 1000 laminar flow, Reynolds number 20,000 turbulent flow. Okay, the profile and the Reynolds number, different Reynolds number will have the different profiles. So here the table I again got from the same book. So I plotted the like put same values, but also we have the V maximum divided by the V average. Okay. So here we can find out the ratio of the V maximum with the like I'm talking about this thing that here the we have the like U mean is equal to 0.5 of U maximum, or U maximum will be equal to the twice the U mean. Okay, point divided 1 by 0.5 will be 2, but here the values are like varying. Okay, so it varies from like a lower on the lower side is a 1.26. This is close to the like a laminar flow, and maximum value that we are getting here for Reynolds number 10 power 6 3.2 million 1.16. Index varies in this way. So we can find out the values of both n and the V maximum. And the V maximum here we need this over here, and this is over, we need it over here. Okay. Now from U maximum, let's say the U maximum, U upon U maximum. Okay, leave it. So this is like V maximum upon the U mean. So this is the, let's say, V maximum upon U mean is equal to 1.26. So U maximum will be equal to 1.26 into U mean. So why we are doing this thing? Because we know the U mean, that is inlet velocity, but we don't have the idea about the U maximum. So in the formula you can replace it when you want to plot that in the Excel. You can replace this one with the Reynolds number is like a 4000. Then you can put this formula there, and U mean is the velocity at the inlet. Okay. So now use the interpolation because our value for the Reynolds number is the 10,000. That is the in between these two values. So use the interpolation to find out the n, and also you to find out the V maximum upon the V mean. So I found out that the n is equal to 6.189, and the value for the like ratio U maximum upon U mean is equal to 1.256. So you can make it 1.254. So put in this formula and then use the Excel to plot this plot over here. Okay. And what I did in the Excel, let me show you. Okay. All right. So here is the equation. Actually, the equation would be this one. Okay, so now I will be starting. So what we have to draw is that we have to draw the velocity. Like there are two ways to draw the velocity. Number one is in this way. Second way is like you do on the pipe. Okay, so in that case, the radial coordinate will be along the y-axis and the velocity will be along the x-axis. So let me show you that thing. Okay. So this is the velocity, and this one is the radial coordinate. Okay. So the diameter is equal to how much? Diameter is equal to the 0.2 meters. Okay. So it means that the radius R, capital R, is equal to the 0.1. Okay. So I start with 0, and then I will gradually or maybe I start with the 0.1. Okay. So 0.1, then I gradually decrease the value. So in this case, this will be the this value minus 0.005. Let's try this thing. Okay. So I have to go to up to the 0. So 0.0, and the 0 is over here. Okay, you can like have the more accuracy, and you can put the like a difference maybe 0.0025, 0.001. It's your choice. Okay, so here we are 1.254, 1.254 into like u mean is equal to 1 meter per second. Okay, and into this is the bracket, so I'm starting with the bracket 1 minus, this will be the r upon r, so this will be the like r divided by this capital R. Okay, and I will close the bracket, but here what you have to put is that you have to put a dollar sign, so this value remains constant here. So and so this is a 1 minus like this value, and then we have the power, that is the, so this bracket and then power, and in the bracket I will write it down 1 upon 6.189 and bracket close, and I will put another extra bracket outside the whole thing here. Okay, so this value should become the 0. So 1 upon r, 1 minus r upon r. So here, okay, this is not 0 because we are putting the value at the cell number not 11 but 12. This becomes 0. Okay, so drag this value. This is exactly a 0, and maximum velocity is equal to 1.25. So this is also confirmed here. Okay, and afterwards what I'm going to do is that I'm going to like put the same velocity profile but with the minus sign. Okay, so here paste the value and put the minus sign here, -1 into this value, and drag it. Okay, so this value will be with the same like values, but this time their value will be now like inverted. So the 0 will be at the point +1, plus 0.1, and also at the point minus 0.1. Okay, so paste the values here and delete them from altogether. Okay, sorry. So you have to put the values like copy them again, and this time just put the value, simply value, so with the numbers here, that's all. Now you can delete these all things from here, and take out these values on the like a top column. Okay, so now I will arrange the value, I will arrange data in the like from like highest to lowest value. Okay, so this will be like a start from 0. So I will start from this point onwards. So copy and paste over here. These are values already there, so there is no need of putting the 0 value there. Okay. So if I plot only half values, like this will be half profile. Okay. So insert chart. This is a half chart here. Okay. So in order to make it complete, like you see in the picture here, so what you have to do is that you have to edit the series and put all the values for the x and y directions. So velocity is on the x-axis, and the radius is on the y-axis. Okay. So there is a kink here in the data that you can see from here as well, like here. If I zoom the picture, there's like a drop in the slope on the top side, same you can see here, and then there's like a change in the slope, and then you will see the maximum velocity with a kink in the profile. Okay, same thing you can see here as well over here. Okay, so this is like a point of discontinuity here, so I don't know that how this problem can be solved, or maybe if I just remove the data point on the 0, and this problem can be solved. For example, delete the like altogether this whole cell. So this problem can be addressed here. Okay, like here. but still there is like a kink here is there. Okay, this looks better actually. Okay, this looks better than the previously. Okay, so like you have to adjust your plot. Okay, so now we have the velocity profile from this equation. Now we will solve the CFD, and then from CFD we have the like a velocity profile that is from the result of the simulation, and that we compare with the analytical this empirical profile with our CFD profile, and let's see how much accuracy we have. And similarly, we will compare delta P pressure drop, and Darcy friction factor, and the coefficient of friction. Okay, so this thing is like written here as well. Okay, so now it's a point. It's like a time to make the geometry and then the meshing. So geometry was made in the design modeler, and one interesting thing is that I use the same geometry that we have in the like laminar pipe flow case. Let me show you that slide. So I highly recommend that you should go through the that workshop before you start here. Okay, so here you can see that I use the same geometry, same file. I just modify the diameter and the radius. Okay, so instead of diameter 1, I use a 0.2, and length is equal to 16 meters. So, and the meshing is done here, and this meshing was done based on the criteria for the turbulence model, and that is that the y plus should be equal to 1, so that we can resolve the viscous sublayer and we can get the values of the CF and the Darcy friction factor very accurately. So you can see the mesh, and meshing was like a very much rigorous that you haven't seen before. So here I discuss about the first cell height. So starting with the correlation for the like CF, that is based on the internal flow, and this is valid for the pipe flows, and this is valid up to Reynolds number equal to 1 lakh. So from the CF, I put the Reynolds number which is equal to 10,000, and the dimensions, other parameters are given here. So the CF was like a 0.007, and the wall shear stress is equal to the like because the wall shear stress divided by 1 upon 2 rho v square is actually the CF, coefficient of friction. So I can solve this one for wall shear stress will be equal to 1 upon 2 rho v square into CF, and the velocity is equal to 1 meter per second, density is equal to 1000 kilogram per meter cube, and I got the wall shear stress is equal to 3.95, and where the wall shear stress would be, the wall shear stress would be on the wall. Okay, that you see the slope here, this one. So if I multiply the partial u by partial y with the viscosity, this is the wall shear stress at the y is equal to 0, or radius is equal to like on the top and bottom. So when the r is equal to r, that is the value we are looking for. So that value we found out from the like through correlations. And one more thing that I want to give you idea, that if you find out the Darcy friction factor from the correlations or Moody diagram, like here, this or this, or this form or this chart from there for different maybe the roughness ratios, and so you can use that value directly here. So instead of using the correlation, you can directly find out the value of F from those correlations or from Moody's diagram, and then use a formula that CF is equal to F upon 4, and from there use the value of CF in this formula instead of using this formula. So directly you can find out the wall shear stress. So which is equal right now with this correlation is 3.95, and the friction velocity, that is the velocity like a scale on the like in the boundary layer, is equal to is given by the square root of tau wall divided by the density. So tau wall divided by density is a friction velocity. This is coming out to be the 0.062849 meter per second, and the y plus is actually your first cell height. So that is the first cell height, which is actually is a here. So this is the actually a y here. So it should be written like a delta y first one, and the y plus value that you are going to be see after like putting this much like first cell height, the y plus will be 1 on the first cell here. Okay, so I use the formula y plus is equal to y friction velocity into density divided by viscosity. And one more thing is that viscosity upon density is equal to the kinematic viscosity or the nu. So you can also change the formula is a y fractional velocity divided by the nu. So either way it will work. Okay. So I put the value, the required y plus is a 1, and the actually this is the in this formula this is the viscosity, which is 0.02, and the fractional velocity which we found out from the correlations and then the formulas 0.062849 into 1000 is the viscosity. So the first cell height is 0.003182224, or you can say it's a 0.3182224 millimeters. So this is the value we are looking for. Okay. Okay, now in the ANSYS meshing, what is the problem is that you will see in the ANSYS meshing part, I will discuss this slide as well. I have divided geometry into 4 parts and 5 parts that you have seen in the laminar pipe flow. We use as like a geometry decomposition and the sieve meshing method. So the actually problem is that in the sieve meshing method, we cannot directly give the fuzzle height. So what we can give the either the there is like a two things, bias factor and the like your ratio, the cell change ratio, means the cell growth rate or cell growth ratio that we can give there. Okay. So formula is that total like the length of the edge, that is like a number of cells you are putting there. If you add all these cells into there, there's a length of definitely the geometry length will be equal to the number of cells total length added. So this is equal to the I from 0 to the n minus 1 summation, and it's L1 into R power I. The L1 is the first cell height that we are looking for. Okay, the L1 is the first cell height, and the R is the like is a varying from 0 to n minus 1, and the n is the number of divisions, how many divisions you are going to put on the your mesh. So right now this is like a 1, 2, 3, 4. So 4 divisions are there. So this is 4 divisions. So in this case the value will be 4, and the R is the growth rate, that the how the first cell is like a given there. The second cell, which is here, how at what rate its second cell, third cell are growing from the every subsequent cells from there. So let's say growth rate is a 1.2. So every like a size of this cell multiplied by the 1.2, you will get the size of the second cell. For third cell, second cell height into 1.2, like a growth rate is a 1.2, you will get the height of third cell. This is how this is going to like a grow. So in this case, the edge length of this geometry right now with this composition, this will vary if we change the decomposition like a parameters. So if I change the like my square like a length, then this will change. Okay. So my length of edge line right now that I'm going to make the mesh here is a 0.0434 meter, and the number of divisions I want is right now 18. So first cell height is L1. So from here I use a biasing factor formula, that is like Ln divided by the L1. This is the last cell which is the here. This is the last cell which is the Ln, and this is the first cell which is the L1. So ratio, the biasing factor is the ratio of the last cell height divided by the first cell height, and this is also equal to the R power n minus 1. This is the growth rate, and power n minus 1, n is the number of the cells here, number of divisions here. So the R is growth rate, n is the number of divisions. So we can solve this formula for the R, and the R will become equal to the bias factor power 1 by n minus 1. And then solving these two formulas, I can find out that the L1 is equal to L L into 1 minus R divided by the 1 minus R power n. So we have this formula for the growth rate, this formula for the first cell height, and so what I did is that I used either you can use like your calculator or Excel sheet, and the second way is that I can use a ChatGPT. So I give these formulas. Okay, so what I given here is that the my division which I like a thought is 18, biasing factor I put here first at the 5, and edge length is like this one. Okay, so with this edge length we can find out the values of these parameters like in this way. Okay, but what I did is that I am saying that the like here that the what I want is that I want that the my first cell height. Okay, let me show you. Okay, the first cell height for the y plus should be equal to the how much? Is equal to the 0.0003 31822 and 9. And the edge length, that the length of the my geometry like dimension, that is like you can find it out from here. So if you click on the edge, you will see the length on the bottom 0.043 and 431. So 0.043431. Okay. And I don't know about the biasing factor should be the what should be the optimum value, but we know in CFD that the your value of the like a growth rate, that is like R here, should not be more than 1.2. So I am setting the my growth rate as a 1.15. Okay. And like asking here the give the number of divisions and corresponding biasing factor. Okay, you can actually calculate that one through the Excel also, but that requires some like numerical methods to solve these equations. So the ChatGPT can give you these values very quickly. Okay, so do use them. So these are our parameters. So using same formulas which are given there, L1 into 1 minus R. So they are computing the L upon the L1. So L is the total length of the edge and L1 is the first cell height. So this is coming out to be the 136.5. So you can now solve this equation. Okay, then this equation contains R in both numerator and denominator, and the R is having power n and the R is power 1 in the denominator. So this is like they are plugging the values and finding out the values. Okay. So what they found is that if they put the value of R 1.15, the 21 point so they are like solving for the n. Okay. So n becomes the here. So n becomes the 21.9. So it means that we should go for not the 18 cells but 21.9 or 22 cells. And the biasing factor is given by this formula, that is R power n minus 1. Okay. So put the value of R 1.15 power like a 21 or 22, whatever your choice is that. So let's say if number of the number of deviations are 22 because R minus power n minus 1 is there, so there was 21 is there. So you can either use a biasing factor of 18.9 or you can use a number of divisions like a 22 will be same there, but you can either use the like a ratio as a 1.15 or biasing factor of 18.9. So what I did is that I used the biasing factor of 19. So you can also, if you change like that one to the smooth transition and the growth rate is 1.15, you will get the same thing as well. Okay, for example here. Okay, compare here and you can feel this is exactly the same thing. Okay. Might be we need to increase the number of cells on the like circumferential edge. That is like a part of the mesh temperance study. Okay, that we will definitely do, and definitely we will go for the more cells here. But keep this thing in mind that if you go for the more cells, then the if you want to keep the first cell height like a constant, then for example, like let me give you idea. So if I want to like increase number of cells, okay, so if I increase number of cells to 30, what would be the growth rate R? Okay, so length is like a same, which we cannot change, and number of divisions we change to the 30. First cell height remains same, edge length is remains same. So what we are concerned is the growth rate. Okay, so growth rate is like around 1.098. Okay, that is around the 1.1. What is corresponding bias factor? So 15. Okay, so from 19 now this becomes the 15. Okay, so actually both things will work. Okay, so here let's change it back to the like a biasing factor. Okay, and click on generate. All right. Okay, then definitely after making the mesh, number of cells are very good and the quality is also very good. So we will proceed for the second thing that I want to show you is that the same thing I use also, but this time I use my own Y plus calculator, and in the ICM CFD that's a use here in this picture, I could like make the directly first cell height I can provide there in the, there's option there, okay. And secondly, the first cell height that I use, another correlation that I can show you, and in the that correlation that is not valid actually for the internal flow, that is valid for external flows. Like I use that one for Hammond body simulation. So this correlation is over here. Okay, another correlation is here. So what I did is that if I put the value of my Reynolds number, which is like a 10,000, okay, and Y plus I want to put is a 1, and my density is a 1000, and viscosity is 0.02, and velocity is equal to 1 meter. So my first cell height would be the with this formula. My first cell height would be the 0.00029 meters. Okay, meters. So how much change is there between the that formula and this formula? There's a change of like here. Okay, so the difference is it's 0.318 millimeters, and here I am getting the value of 0.2950. So 0.2950 and 0.318, they are almost close. Okay, and if I use another correlation like which I've shown you in the chat GPT, and similarly here 10,000. Y plus 1, density is equal to 1000, viscosity is the 0.02, and velocity is a 1 meter per second. So this correlation is giving me the value of 0.0003. So this is like these are like in between, this value is like this value is in between these two correlations. Okay, so in this way we found out the value of our first cell height and the other parameter in the ANSYS meshing. So now we are confident to give this parameter and get the very high quality mesh from the ANSYS software. Okay, then what I did is that we can solve, now we are going to solve this with this mesh, and also I use a second mesh that I will provide you, and that you can use yourself, and that is going to be part of the assignment as well. Okay, so in these meshes, I use two meshes, Y plus 1 and Y plus 10, and both are with a realizable K epsilon model. These are axial velocity profiles. This is the radial velocity. This is the axial velocity profile. This is the radial velocity profile, and we compared our data with this correlation as well. And you can see there's a difference over here. Okay, here and here as well. The CFD is giving us the very close to the data we should expect from our simulations, similar to the what we have seen in these graphs. Okay, then we compared, this is again from the ICM CFD mesh file. So we compared the F, which we can directly find out from CF. CF we can find out directly from this formula. So the CF is equal to the F upon 4. So this is from empirical formula, SE Holland 1983. And from CFD, the CF is equal to 0.008573. So error is like 18%. And that's not a very big error as compared if you compare with a turbulent flows. As I told you, the turbulent flows has a lot of assumptions are there, like in the turbulence modeling, in the meshing as well. So this is all about this whole this course. Okay, so you should expect these things in this course. So this is going to be very interesting course, and you will learn a lot of things there. Okay, thank you.